Welcome to the NAND game. As you can see from the instructions here, we are going to build a computer starting from basic components. The game consists of a series of levels. Let's see them right here. We're in logic gates to start. In each level, you are tasked with building a component that behaves according to a specification. This component can be used as a building block for the next level. All right, our first task is to build a NAND component. So we have to connect the inputs to the output, and we have to use these relays in a way that our two inputs will output the correct output. So if it's 0 and 0 and the inputs, then the output should be a 1. So click to drag the components. Okay, there we go. We just can drag it on like that. And if we want to connect it like that, and that is how we hook up our relay components. So fun fact, relays like this were actually invented like a long time ago, maybe like 150 years ago. They were mainly used for telegraphs, I think. It took a long time for people to realize that you can actually hook up relays like logic gates and, essentially create a computer. Of course, computers don't use relays anymore. They use transistors. But the idea is actually the same. All right, so we need to create a NAND gate. So when they're both off, it's on. When one of them is on, it's on. And when they're both on, then it's off. Okay, so this one disconnects when there's a current on C, and this one only connects when there's a current on C. So I think what we want is this one that only connects if there is power to C, because that way we get something like this. Now this looks like totally wrong, but what we actually have here is the backwards logic. So if both of them are 1, then the output is 1. In every other case, the output is 0. That's the exact opposite of what we have here. So this is effectively an AND gate. But what we need is a NAND gate, which is not AND. So we end up just needing to negate this output, and we should get what we want. Now, how do we negate the output with just relays? We should just be able to add another relay. Maybe, I think we want this one. If there's a current on C, then it disconnects. So we can just hook up, I think, straight power to this. And there we go. This is like an inverter now. So if we hook this up, it should give us what we want. So we have an AND gate right here and an inverter right here. So an AND gate plus an inverter is NAND. All right, level successful. And we got the simplest possible solution. Awesome. Your next task is to build an inverter component using the NAND component. Now we just built an inverter from relays, but this shouldn't be too bad either. For this level on, we don't need to consider mechanics of underlying switches, so we're not going to need to use any more relays. While a physical NAND gate requires a connection to a power source, we don't need to show this on the diagram. All components are considered implicitly connected to a power source. We can now concentrate on the logical input-output. So an inverter, right, if our input is 0, we want to output 1. If our input is 1, we want to output 0. It's actually pretty easy. We just can do this with one NAND gate. You just hook up both inputs. You just hook up both NAND inputs, A and B, to the one input, and then you hook that up to the output. And this should give you what you want. Yep, check solution. This is optimal. Next level. Next task is to build an AND gate using only NAND and an inverter component. You might not need to use both kinds to solve this task. So NAND, as I talked about before, is not AND. So all we need to do to create an AND gate from NAND is to do a double negative, not and. So we do an invert, not and. So we're kind of doing not and. Hook these up like that. And there we go. This should work. So we're just inverting the NAND to make not and. All right, this is optimal. Next level. Okay, so it looks like we're making OR now. So OR, the way OR works, if both inputs are 0, then the output is 0. Otherwise, it's always going to be 1 for all the other input combinations. Now, if you look at the NAND gate, you'll see it's kind of like a mirror image of the NAND gate, where here we have 0, 1, 1, 1, and here we have 1, 1, 1, 0, right? It's just a mirror image. It's not inverted, it's just flipped like a mirror. And if you want to flip things like a mirror, the trick here is that you want to invert the inputs. So we need 2 inverters, invert A and invert B. And this should give us our OR gate. And there we go, we got the optimal solution. Next level, XOR. Now XOR is exclusive OR. Our output is 1 only when only one of the inputs is 1. If both of the inputs are 1, then the output is 0. If both of the inputs are 0, the output is also 0. Exclusive OR, one or the other, not both. This should be pretty simple now that we have AND and OR. What you can do is you can just focus on the output scenarios. So 0 and 1, we want the output to be 1. So if we put an AND here, we want B to be 1, so we hook that up. And we want A to be 0, so we can invert that. So not A and B should give us that one. And we want the opposite. We want A and not B. And we're saying either this scenario or this scenario will work. So we just OR these together. And then we could hook that up to the output. All right, now I doubt this is the optimal solution, but let's check it. Yeah, 5 components used. It is possible to solve this using fewer components, but I think this is like a really straightforward way of understanding. We have not A and B, or A and not B. So you can see how that looks compared to here, not A and B, A and not B. And there we go, next level. Well, actually, that's it for logic gates. So we're going to stop there for now, and then we're going to start arithmetics next time. Thank you guys for watching, and I will see you for the half adder.